This is sections 8.4, part 3. So again, we're dealing with the trig with the integral that often involves a square root, although it doesn't have to be. Then we can use the trig substitution to get rid of the square root. Now we're looking at number 6 right now. You see that we have 1 over square root 2x minus x squared. Now this one is a bit harder. When you use a trig sub, we have 3 choices, right? But then we often have the difference of squares, sums of squares inside the radical when you try to do this trig sub. But that one doesn't have one, right? It doesn't have that form. So in order to do this, we have to do things on the side first, try to make the quantities inside the radical a difference of square. To do so, we have to use the techniques called completing square. Complete square. Okay. So we need to use the complete square techniques here to do that. So let's look at the part of the radicants. Okay, so 2x minus x squared. 2x minus x squared. It's not so nice. Let me rewrite it. So it is 2x minus x squared. Okay. Now, first notice that when you complete a square, we need to rewrite with the quantity in the decreasing order of the power. Okay, so we write it negative x squared plus 2x. And one more thing is we need to have that to be little coefficient to be 1. So in this case, I'll take out the negative, and so we left with x squared minus 2x inside. Okay, so see that, and x squared, take out the negative, so x squared minus 2x. So he is the magic number that we need to add to make it perfect square numbers. The way we do again is to take half of this, which is -1, you square is +1. So I add 1. Now as I add 1, he's inside the parentheses. If you multiply that out, you see it becomes negative x squared plus 2x minus 1. Right, so basically we end up with an extra -1, and to cancel that, you should have a +1 outside, so that's equal to this quantity. But I introduce a +1 inside, so we can have a perfect square trinomial in here, and that is x minus 1 quantity squared, and then there's a +1 outside. So now you see they have 2 quantities here. If we flip, so we'll put the 1 in front, so you can see this is 1 minus x minus 1 quantity square. All right. So now I have a difference of square after some hard work, right? So when I rewrite it, write this is now an integral of 1 over square root of 1 minus 1 x minus 1 squared. There is x minus 1 quantity squared dx. Okay. Now, that one's still a bit different from others because of the instead of 1 minus x squared, right? 1 minus x minus 1 squared. So think of this as a quantity, x minus 1 here. So again, in order to use the trig identities, the trig substitutions, it doesn't quite follow the form yet. So there are 2 ways to do from here. So either you do a substitution first, you let u be x minus 1. So it's going to turn into 1 minus u squared, and you can use the form. but I'm not gonna do that step though. I think it's probably easier here to think about this. You want the trig identities there, so 1 minus what squared, right? So this quantities, if it were sine, right? Remember we can do sine, tangent, secant. In this case, seems like you want 1 minus sine squared. So that suggests, okay, so that suggests here we could try let x, let me try the different colors here, maybe it's yellow. Let, instead of x, I want x minus 1 to be sine of theta. X minus 1 to be sine of theta. So if you let x minus 1 be sine of theta, you can solve for x. That would be sine theta plus 1. Again, I'm trying to take the derivative. So derivative of x is cosine of theta d theta. Again, what I want is when I substitute in, I got the perfect identities inside. And now I got what I want. Look, 1 minus, remember the x minus 1. The x minus 1 is sine theta. So that is the sine theta, right? And don't forget that it's a sine theta square. The dx, it's a cosine of theta d theta. So see, I change the variable. And once I change the variables, I'm in a different world, right? I'm in a variable theta now. And in this case, not sure what color I want. Let's do blue. Right, so we're in a new world. In this world, everything in terms of theta, you have 1 minus sine square inside, and that is square root of cosine square times cosine theta. Right, so 1 minus sine square is cosine square. And the integrals of this, right, you can simplify. The whole point of doing that is we simplify till we don't have radical. And you see, square root and square cancel, and you time cosine of theta d theta. And how to integrate that? Cosine theta, you see, got cancelled, right? The cosine theta, you got cancelled. So your integral just become what? Just 1. Just 1. So what is the antiderivative of 1 with respect to theta? All right. So we know it's gonna be theta. Okay. So now we are in again a different world in the theta variable. So it's gonna be theta plus c. Theta plus c. Now, how do you convert back from theta to sine? And again, don't forget that these are the relationship that we have, right? X minus 1 is sine theta. So if you take the inverse side, solve for theta, then we have the inverse side of x minus 1 is theta, or the arc side of x minus 1 is theta. Okay, so we're now back to original variable here. So that is arc side of x minus c plus x minus 1 plus c. And that is our answer. Okay. So that's number 6. Now it's on to the last one, number 7. The integral of 1 over 4x squared plus 4x plus 2. Now I see that one looks very normal. So in the sense it doesn't have square root. Normally we do. But the trig subs also works very well for that one. And again, to use the trig sub, you might want to put it in the form. We always need difference of square, sums of square, and we don't have it here. And same as number 6, we will need to do a complete squares on the side first before we can apply the trig sub techniques. Okay, it's a complete square. So you look at the denominators here, 4x squared plus 4x plus 2. To complete square, again, you need to have that written in decreasing order of the power. Now, step 1, which it is. Step 2 is you're going to need to make sure the leading coefficient is 1. In this case, not. So we're going to factor out the 4 from the leading term there. So it's going to be x squared. And that becomes just an x. Now, one thing to keep in mind, when you try to complete a square, the constants do not put inside, we leave it outside. Okay, so we will figure out what constant we add here in order to make it a perfect square trinomial inside. With the same trick, in this case, it's 1, right? So take 1 divided by 2. So that'll be 1/2. And you square, so it's going to be 1/4. So I'm adding 1/4. Adding 1/4 inside of the parentheses as you multiply it out. It will be 4 times 1/4. So we're actually adding an extra 1 in the forms of 4 times 1/4. So we need to subtract a 1 in this case, okay, a 1 or 4 times 1/4. Make sure you multiply it out and cancel to see if that equal to original expressions, right? So after I do that, then you see what's inside now is a perfect square trinomial. So that would become x plus 1/2 quantity squared plus 2 minus 1 there, it's 1. Okay, so that by like term, and this becomes that. Now you see we have a perfect square, so the sums of 2 square. We put a 1 in front, right? So we're gonna have 1 plus 4 times x plus 1/2 quantity square. Okay. Now from here, you're going to decide what you're going to do using the sine, tangent, and the secant. Notice that this is the sum of squares. So with sums of square, you know you'll be using the tangent. But again, it's a little bit tricky here how to figure out the tangent. So just want to know, like, figure out by looking at what we want, okay? So remember, we want identity. So the identities that we have using is 1 plus tangent squared equals secant squared here. And you see that's 1 plus. So you know that you want this quantity to be tangent squared. So what I actually do is I'm looking at this, right? So tangent square is going to be this whole thing. So how do we make it works? Well, if that equal to tangent square, or this quantity to tangent square, then isn't it the quantity here, the 2 times x plus 1/2 has to be tangent. You see that? So what I'm saying is, I can see if you do the trig subs there, then the 2 times x plus 1/2 is tangent theta. It's tangent theta. You see that? Okay. Why? When you square this, you have 4 times x plus 1/2 square equal tangent square, right? Now, then you're solving for x. Actually, you need to solve for x, so you take the derivative on both sides. So if we solve for x divided by 2 first, we can multiply first, maybe multiply it first. So you're gonna have 2x there, okay, and then plus that's a 1 equal tangent of theta, okay, and then subtract 1, we got 2x equal tangent theta plus 1 divided by 2, so x turned out to be half of tangent theta plus 1. Okay, again, why solve for x? Because I want to take the derivative dx. So derivative of that is, derivative tangent is secant squared. Of 1 is going to be 0, so dx is half secant squared d theta. Now the integral at the beginnings, I didn't write that step. I should write it here. After you complete the square, you see that the denominators become 1 plus 4 times x plus half square dx. So if you simplify from here, I mean if you substitute in from here, you see 1 plus this quantity again is tangent square. That is 1 over, change it to be 1 plus, change color, so that's tangent square there, and then you time dx is half times secant square. Okay, so you have tangent square, right? So now we are in a different world, right? So now we're in a different world. We can integrate this. Maybe I change. Just leave it black. So 1 plus tangent square is secant square. You see that? 1 over 1 plus tangent square is secant square. And then you time half of secant square. Then secant square cancel, you left with 1/2, and of course I can integrate a half. So it's constant, so it will be what? 1/2 theta. 1/2 theta. Plus C. And the final step, T is write the theta, right, in terms of x. And here it is again, we're looking at that. So this expression become, if you solve for the theta, you have the arctan of 2 times, let's multiply that out, so you should know in parentheses there. All right, if you multiply this out, then you have 2x plus 1. So arctan of 2x plus 1, so looking at these, maybe it will be theta. So your answer will be 1/2 times the arctan of 2x plus 1 plus c. And that's finished. The last example here. Okay. Now, one thing I want to cautious is the technique here when we do. Sometimes we don't have radical like this, and we can still do it, right? And other times it might be in disguised form. So if you do homework, you might not see the exact form that we did. It's just because sometimes you might see the integral that's the form where it's just the power, right? So instead of like 2 over, you might have 4x squared plus 4x plus 1, say to the 3/2 power. That's also a trig substitution, right? 3/2 powers, or sometimes you even have like the negative powers, so it looks like 2 and then x squared plus x 7 to the negative 1/2 power, right? So that it just run over the square root, so it's also could be done, right? So it could be done with the trig sub. And finally, do not forget that whenever you have those radical that you have to use the trig sub, like in many cases where I can tell easily that this is not a trig sub problem, and do not attempt to. Okay, even look at square root, because I can see x squared minus 6 and then 2x with the derivative this. So this problem, that one right here, a u sub is quick and easy. Okay, so do not use the trig subs. The 2 up here, the trig sub must be used. Okay, that finished the last section, the last part of the 8.4.